Good morning, everyone. Can you please confirm if you can hear me? Awesome.
Yeah, Enoch, do you want to run that?
Yes, I'll just run.
Yeah.
So, even yesterday, we conducted a quiz wherein we posted the question on both Facebook and Instagram and LinkedIn, and many of you responded and participated in it. So, what we are going to do right now is we are going to pick a winner, and then we are going to give them a surprise gift. So, to do that, let me share my screen. And right now, I believe you should be seeing my screen. And we had about 183 people participate in our quiz. So we are randomly going to pick one person. So for that, I'm using the random number generator. So 1, 8, and 3. So you can see the last number is 183 and the first number is 1. So the moment I click on generate, whatever is the number that comes up, that person is the winner. So let's do this. 3, 2, 1, and go. So it is the number 58. So let's see who our lucky person is. Right. It is Sunita Akula. Sunita, congratulations. You have won our lucky prize for today. And we have your details, and our team will get in touch with you and they will give you the details on how you will get your gift. And thank you so much, guys. And even today, we'll be sharing a quiz right after our session. So make sure you participate in that, and you'll also be eligible to win prizes like how Sunita Akula did today. And thank you so much. And over to you.
Thank you, Enoch. And congratulations, Sunita. Good job. And I request everyone else to be active, because these quizzes are not just for winning these kind of prizes, etc., but the quizzes are also meant to bring in some kind of interesting aspects. When you start answering the quiz questions, it'll be a kind of recap of the session that we have discussed, right? For that reason, you have to do that. All right, I think this helps. Let me share my screen and then we'll proceed further. Even before that, Enoch, can I have the YouTube video, yesterday's video link? Maybe we will have to post it on the sticky note.
Sure.
Yeah.
It's there.
Naga Sai Babu is asking for this. So wonderful. We will share with you. I would directly share with you the mind map, which got updated here. Okay, there we go. So everything that you need, you just need to double click and you'll be able to access this. The same mind map that I've discussed yesterday, each and every point is listed down here. Okay, you might want to just minimize it, zoom in, zoom out. Yeah. If you want a link to this, I would certainly share, but I would like to do a recap on this. But oh, sorry, I'm not sharing my screen. My bad. You wouldn't have seen that. Okay, here we go. This is a mind map, which I'm speaking about. Practical AI and deep learning. I would share this link with you all now, but before that, let's look at this session. So all the sessions are available here. Today is day 12, right? This is day 11. Until day 11, we have the details. Watch it. Trust me, you will be learning a lot. Of course, I would not claim that you learn 100% of AI and deep learning, but at least you would have covered 50 to 60% by the end of the training. And remaining things, of course, are part of our mainstream program. So you'll be able to learn that. So let me also post this. And please do not forget to subscribe, because I'm not asking that to do it for my purpose, for your own purpose. Whenever we do YouTube live next time, if you want to be notified, you just need to click on this button. That's it. Just click on this subscribe. That is all you need to do to be able to get access, okay, to be able to get access, right? This part. Okay, and a few of you all are reaching out to me asking for my, you all are saying that, hey, we do not have LinkedIn account and we don't want to create either. How do we connect? Right. I shall share with you all my details, but then I'm not sure whether that's, I log in here. I didn't log in, so I'll share it. By the end, I will share it. No worries. So videos, no questions. I'm sensing, assuming. All right, and that is not possible, Vishnuvardhan. We will share on the website itself. You can have unlimited access. See, learning management system, we are going to disable that after a few months. Okay, maybe 6 months or so. Then after that, you'll not have access. But when we give it here, you will have continuous access throughout your life, and any future updations, you'd be able to see it here. There are algorithms coming at the blink of an eye, right? Just blink, there are new algorithms coming in. So that's the idea. All right. Hope that answers your question, Vishnuvardhan. Okay, let's proceed further with the recap. So we started off by understanding about high-level project management methodology, CRISP DM. We understood the business problems. We created the project charter, right? And then, I mean, you need to create. We didn't create, but we need to create. But we understood that we need to record the business objectives and business constraints. Then you need to proceed further with data collection. Even before you proceed further with data collection, one should be aware of the various data types. And we discussed to a great extent about the various data types. And then we got into primary and secondary data collection mechanism. How do you do that? Once you're done with that, you cleanse the data, you prepare the data. That is also called as data munging or data wrangling. Exploratory data analysis, feature engineering, bunch of these. And then you proceed further with data mining or machine learning. In this, we have supervised learning, unsupervised learning, reinforcement learning. We'll get there. We are now discussing about supervised learning, predictive modeling, neural network. We are discussing about convolution neural network, CNN, videos and images, right? And we will also discuss about recurrent neural network and all that. Here we will add more. We will add more information, right? Like what we have been doing. And this is a one-stop solution, even when you want to do any projects or for your students. We have discussed about deep learning primer, all of these. We discussed in detail about various activation functions or transfer functions which exist. And then we discussed about optimization algorithms. I will add more information about each and every optimization algorithm also. Then we know the various deep learning libraries that exist. And we discussed about the various deep learning challenges and practical issues that exist and how do we overcome those. Post that, we switch the gears to discuss about computer vision, wherein we discussed about elementary applications of image processing and video analytics, challenges, what are the features that you can extract, what transformations we can perform, how do you reduce the noise, the various kernels or filters, cross correlation, convolution, boundary effects, template matching, upsampling and downsampling. Yeah, we have discussed about that, and we have looked at OpenCV library, and we have done bunch of these. And then we switch the gears into convolution neural network. There are a lot of things that we have discussed yesterday about convolution neural network. What are those? We discussed about how you will have an image, which is an input, and how we apply convolution layers, or how do we use conv 2D filters. And when I apply a convolution layer, when I convolve it on the image, we also discussed on what will be the size of the output. And we also discussed that the number of weights or parameters that your model is going to learn, okay, would be correlated to the size of your convolution layer. If you have a 3x3, then you learn about your model will learn 9 weights, so on and so forth. We have also discussed about another concept called as stride, and the formula to calculate the output size, which is n minus f divided by stride plus 1. You can have stride equal to 1, stride equal to 2, stride equal to 3, so on and so forth. We have also discussed about pooling layer, in which we discussed about average pooling, max pooling, L2 pooling. Majorly used is max pool. If you apply pooling on your images, what would it do? That's a question. Let me put it here. So here's a poll question. Let me ask the question on. If we apply pooling layer on an image, what will happen to the output image? Would it downsample or would it upsample? Yes. Can you all please respond to this? Will it downsample or upsample? Absolutely. It will downsample the image. It will reduce the size of the image, basically. Wonderful. Where are we here? It will downsample. Absolutely right. And we discussed about batch norm. Okay, so you'll have typically conv or conv relu convolution layer, followed by activation layer, followed by convolution layer, followed by activation layer. And if you want any pooling layer, you just add it here, so on and so forth. And finally, you end it with a fully connected network. This is a typical sequence in which you define your convolution network. Convolution neural network is also called as convolutional neural network. Don't get confused. These are all different names. okay, is also known as conv nets. And when you're applying this in an image, since images are of two-dimensional, you call it as conv 2D also. Because you might be reading a lot of books moving forward, and whatever book you see, this is something that you need to bear in mind. Okay, next. I'm going to open the code, and in parallel, I am going to explain you all the code and the theory. The code and theory. That is how we are going to deal with this. Somewhere I've seen CNN here. Let me. This would be a different file, which is. Let me try out. No, this doesn't help. Yeah, here we have the complete CNN code. So I'll copy this, and then from now on, whenever we work, we will be working on GPUs. I have a GPU computer. This is a GPU machine, and I'll show you how GPUs are uh, going to come into effect, right? But before that, if at all you need this link, do not open it now. You can open it at a later point of time, but then that's the mind map. A few of you were asking, so there you go. We'll be updating it throughout, so please keep it handy with you, and it is going to help you a lot. You can bookmark it. You can bookmark on your browser so that you continuously have access to that. Not just this, we are bringing in IoT, cyber security, cloud computing, all the mind maps in a very detailed manner. So you'll simply enjoy it. And also, we are bringing in the interview questions for our students so that they find it easy to crack interviews. All right. So here, import TensorFlow as TF. TensorFlow is a deep learning library, and you can import it as anything. Basically, you can give TF, or even if you do not want to give this as TF, it is fine. You're importing TensorFlow, which is a deep learning library. In case you say as TF, from the next time when you use any of the functions within TensorFlow, you need not give the complete name. Instead, you can say TF. For example, here, tf.test is GPU available. When you work on GPU machines, you will understand that you will also have something called as CUDA, CUDA. You need to install that. Okay, and then what is a minimum compute capability of putting none? And I didn't import this. So I'll select this and run it. If it says true, GPU is available. If it is false, GPU is not available. What does it say? True. Wonderful. True means it also has given true here. Okay. True means GPU is available. I can show you by going to the task manager. Control Alt Delete on your keyboard will take you to this screen. You need to click on task manager and go to performance here. And look at this GPU here. NVIDIA GeForce GTX 1660 Ti. This is by far the simplest of the GPUs. Okay. And for a commercial purpose, we use Tesla. But then if you are planning to upgrade, and if you are hell bent upon having your own physical laptop, then go with NVIDIA 2080 Ti Max. This is what we have given to our employees because they keep working on deep learning projects. So this is what they use. But it caution and okay. With respect to RAM, it's 32 GB RAM, and this, of course, we can expand this to 64 GB also, and you can increase the number of GPUs as well. Okay, so I would suggest you to go with the desktop version if at all you want this. For us, we have the laptop versions of this because we need to do client presentations. We need to go to client locations. Yeah, that is the reason why we have this. But otherwise, yeah, it's a desktop version. Next thing is, one second, let me make a note of this. Okay, sorry about that. Whenever I keep getting ideas, I keep making a note of that. Okay. And this is one version. If you feel that, it will cost you at least 2 lakh rupees. If you feel, no, I do not have 2 lakh rupees, then I would suggest you to make use of Google Colab. It is very, very easy. Each line of code, you can run it in Google Colab, and they give you, I think, 8 GB RAM and a basic GPU version. You can run your programs there for practice. Up to 300 GB, up to $300, it is free. So use it, that's okay. And if you want to upgrade this, then you need to pay to Google. If you don't want to upgrade, if you want to use a base version, you need not pay even a single rupee because this is free. So it's like, just simply put, the interface look and feel will be like this. You just need to execute these lines of code in Google Colab. Or if you're bent upon, no, I want an advanced version, then bring your own cloud concept is coming into picture. As I've told you, you upgrade it. If you want, say, 64 GB, say I want 64 GB, I want a 2080 Ti Max to be able to practice, go ahead. Go ahead. It will cost you much, much less. And you know what? You can use this only for the time you need it. Say you use this for 1 hour and you're done with your program. Stop it. You'll have an option to abort or terminate your session. Terminate your session and job done. Okay, again, you can, whenever you want, again start it. So you will be charged only for this 1 hour. Okay, but you have to be careful. If you do not stop it, if you do not terminate, the session will continue and you will be charged extra. Okay, so please. Sorry about that. Okay, so let's proceed further then. We have different versions of TensorFlow. Now the current versions that are being used is TensorFlow version 2.x. Okay. TensorFlow 2.x. And in TensorFlow 2.x, naturally, this is from Google, they are saying that there is a tighter integration with Keras, and Keras is a high-level programming language. So that is why you are saying TensorFlow.Keras. There's a tighter integration with Keras now. So you can write high-level program, means very easy looking program, And in the backend, it will go and execute the code using TensorFlow and give you the results back. So TensorFlow would serve as your backend, and Keras will serve as your front end. So from TensorFlow Keras, you're importing the layers, different layers, hidden layers, input layers, etc. And from TensorFlow, we are also importing models, different architectures. Then you're saying, I want a sequential model, wherein I'm going to take the input layer, which is of size 28 by 28 by 1. Once again, the underlying data that we'll be using is MNIST data, Modified National Institute of Standards and Technology, which gives you handwritten digits. Handwritten digits. And we will be making use of these handwritten digits. And given an input image, handwritten image of 0 or 1 or 2, you need to classify on whether it belongs to 0 or 1 or 2 or 3, 4, 5, 6, 7, 8, 9. You have 10 classes, right? All these images are of size 28 by 28 and they are of grayscale. They are of grayscale. 28 by 28, grayscale means 1, color means 3. Okay, so you have image height, image width, and image channels. Okay, if you have a color image, this will become 3. 3 because you'll have red, green, and blue. And you're taking this input image, okay, and you're using 32 3 by 3 convolution layers, conv2D filters, 32 3 by 3 filters. Okay, and we are using activation layer ReLU. What are we doing then? We are taking that. Look at this. It says conv2D, 2D because it's two-dimensional. Then what are you doing? You are adding another layer, and this time you're adding maxpool 2D. Again, it is of size 2 by 2, 2 by 2, and you are going to apply it on the input image. And out of all these 4, if this is your image, and if you are going to apply this patch here, then you're going to choose the maximum value out of this, and then you'll get the output image, which will be a single value. So the size of the image would obviously reduce, and that is the use of this max pool or any pooling layer. What will the pooling layer do? Pooling layer is going to downsample your image. Okay, it is going to downsample the image. Then you are adding another. See, max pool, in this, your model will not learn any parameters. Here it will learn weights or parameters. Okay, it will learn weights or parameters, but here it will not learn any weights or parameters no weights or parameters are learned. Then you're adding another layer to this. This time you're adding convolution 2D layer. You're adding 64 3 by 3 convolution layers. And activation is once again ReLU. and you're adding it back to max pool 2D of 2 by 2, you're again downsampling the image, and then again you're proceeding further with conv 2D. Again 64 3 by 3 activation is ReLU and model dot summary. So if I were to run this, you'll get to see on what layers are added, how many weights your model is learning, etc. This might not be very clearly visible for you guys. Okay, but then there is 320 given here. Why 320? Why 320 parameters are learned might be a question that you need to answer. Okay, so let me tell you. There are 32 3 by 3. So if you have a 3 by 3, okay, then how many weights your model will learn? 9. Plus there will be one bias. Bias also will be there. So 3 by 3 means 9. 9 plus 1 is for bias. So in total, the bias is also a form of weight. So in total, you'll have 10 weights. 10 weights into 32 such layers will be 320. And I've also told you that when you use a max pool, there won't be any additional weights that your model will learn. So you'll have 0. Okay. Now, if you keep increasing from 32 to 64, your algorithm will learn more representations. Representations means it will learn more features of your data. Then, if you look at the final, let me take it here. Okay. When you look at the final, output here, output tensor, it is of dimension 3 by 3 by 64. Okay, it is 3 by 3 by 64. What you are going to do is, if you have it in this format, you cannot give any output. Your output is determine whether a handwritten digit is 0 or 1 or 2 or 3 or which number it is. But if your data is in this format, 3 by 3 by 64, it cannot be supplied to the output layer. Okay, because it's in different format, output is in a different format. You need to convert this into a 1D format, one dimensional, to be able to give out the output for each neuron. So what we do is, you take this output tensor and you supply it to a densely connected network here. And these classifiers process only one-dimensional vector. However, the output here is a 3D tensor. This output is 3-dimensional tensor. You want to convert that into a one-dimensional tensor. To do that, we are flattening it first. When you say flatten, it will just multiply and flatten it. Okay, once it flattens, so you just multiply 3 into 3 into 64. What would that be? 9 into this, it will be 576, right? So you take this 576 and that would be the input which will go to your flattened layer. Your flattened layer will not learn any weights. No weights are learned. Each and every point is important, friends. Okay. Then you're taking that and supplying it as an input to 64. So 576 going as an input to 64, you know how many weights are going to be generated. Okay, and it'll be 576 plus 1 because there'll be a bias into this. And you're using ReLU activation function. And finally, what we are doing is we are adding it to another dense layer, not conv layer, not max pool. It's dense layer, dense network, or fully connected network, meaning you'll have the layers in this way. You connect everything to everything. Okay. And why are we having 10? Because it is a 10 class problem, 0, 1, 2, 3, up to 9. You'll have 10 total. So you have 10. And you're using softmax. This we have discussed umpteen number of times, right? That if you have multi-class classification problem or discrete output with more than 2 categories, you use softmax. So let me run this part. Oh yeah, yes, my calculation was right. It's 576, 3 into 3 into this. You're flattening, and flattening layer will not learn any weights, and you're supplying that to next layer. So this is what is happening. You're getting 576 and you're supplying it to the next layer, which has 64. Okay, which has 64 neurons. Then you'll have an additional neuron, right, which is called as bias. So this bias also will give input to all the 64 neurons, and each of these 576 neurons will also go as an input. So 576 plus 1, which is 576 plus 1, which will give you 577 into 64. These many weights your model is going to learn, and that count is here, right? 36, 928. I'm assuming it should match roughly. Okay. Then what you're doing is you're giving this as an input to the next layer, which has 10. Why 10? Because it's a 10 class problem. And each of these 10 neurons will spill out an output. And each of these outputs will be probabilities. Each of these outputs will be probabilities in that way. All these 64 neurons will go as an input to each and every neuron that you're seeing here, because it's a fully connected layer or a dense network. Plus, you'll also have a bias. So 64 plus 1 will be 65. 65 into 10 will be 650. Okay, this is how the number of weights are calculated, or parameters are calculated. And if you observe here, you get to see the total number of parameters that your model learns. Trust me, if you would have used MLP for this, multi-layered perceptron, to deal with images, the number of weights would have just exploded beyond imagination. Beyond imagination, it would have exploded. Okay, fine, that's one thing. Now that you understand about how to create your convolution layer, how to make use of max pool to downsample the image, how to flatten, how to add the results of convolution layer to a dense layer. Now let's take the data set. And this time what we shall do is we are going to pre-process the data set. Okay, pre-processing data preparation is very important, right? And that is what we have learned, that after data collection, the next thing is data preparation, which is also called as data pre-processing. So in order to pre-process, first of all, we need the data, and we know for a fact that MNIST dataset is inbuilt in Keras. So we will first make use of that. So we will import MNIST dataset. And within Keras, utils, like utilities, we have something called as two categorical. I'll explain about all these things. Too categorical. And then I'm loading the data set, MNIST.load underscore data. And once you get the data from Keras, you're splitting that data into training and test. That's how the data set is already, the data set which is placed in Keras for your use already has data which is split in training and test format. Okay, so you have the training images. Images are like inputs and training labels. This is like your output. So you have your input and you have your output. Then for test data also, you have test inputs and test outputs. Okay, and then you're doing the reshape, meaning all you're saying is a few of the images. Okay, in the training you'll have 60,000 images, handwritten images. In the test data you have 10,000 images. Each image is of size 28 by 28, and since it is a grayscale image, you have a 1. So you have 64. So what you're doing is you're saying take all the training images and I want to reshape each and every image to 28 by 28 by 1. Why? Say accidentally a few images are made of dimension 26 by 26, or maybe they are of size 30 by 30, or 29 by 29, or 28 by 29, whatever be it. We want to reshape that to 28 by 28. We want every input to be of the same dimension. Only the input layer, the number of neurons are fixed. The number of neurons, because you need to define here in that way. You have to give the input shape. If in even a single image is of different shape, your algorithm will start throwing error. And you don't want that, right? You don't want that those kind of errors. So to counter that, you're ensuring that all the images are made of 28 by 28 by 1. This is number one. Number two, when you have your input layer and when you have your, say, hidden layer, you supply the data in this way. All neurons will be connected to all the neurons in dense network. Okay, I'm just giving you an example of dense network, okay, in this way. Okay, so here, all these weights which are going to be assigned, weight 1, weight 2, weight 3, all these weights could be in decimals. Not could be, it would most often they're not be in decimals. And this could be minus 1.68, some numbers, some randomly chosen numbers initially. Now, when these are in float format, decimal formats are called as float. Float 32, 64. 64 is for a different version, but 32 is a better version. It is compatible with all the old computers also. So we use float 32 to be on the safe side. Maybe 10 years down the lane, float 32 won't be there. Only float 64 will be there, because by then everyone would have upgraded their computers, etc. All servers and all that. But that aside, if you have your inputs here, which are of integer format, what are integers? 1, 2, 3, 4, 5, whole numbers are integers. If you have your inputs as integers and the weights as float format, when you want to multiply x1 into w1, right, or w1 x1 into plus w2 into x2, when you do that multiplication, and if you multiply the float with integer, it will throw error. Hence, what you're doing is weights will anyways be in float. You cannot do anything with that. That's how neural network works. The only thing where you have complete control is on inputs. So you are going to convert your inputs to float 32 format, so that when the integers get converted to float 32, And if your weights are in float 32 format, when you multiply these two, it will start working. It will start working. And then you divide it by 255. Pixel intensity values range from 0 to 255. Okay. And we want all these pixel values. A few pixel values might be 240, a few might be 10. We don't want such a large difference in the pixel intensity values. When you divide by 255, what happens is you're dividing 0 by 255. You're going to divide 255 by 255. Each and every pixel value, you divide it by 255. When you do that, 0 by this is 0, this by this is 1. There you go. So you're reducing the range of pixels to 0 to 1, and this is called as normalization or standardization. When you have data in smaller range, then what will happen is on your error surface, you will be able to reach to the minimum error in a faster manner. Okay, this is the reason why we divide it by 255 and we normalize it. Okay, so this is all about your inputs. Okay, you're taking your inputs, you're reshaping that. Okay, and then you're converting the data to float format and you're dividing it by 255, which is called as data pre-processing. What I shall now do is I will open the mind map. I don't know whether I updated this. Okay, and then I'll type these steps so that you're not confused. Okay, let it be there because this is what we have done first. Okay, then it's fine. I will zoom it. Okay. So here we have the CNN part. What do you do first? Let's understand. So first, understand the business problem, then perform data collection. And once you get the data, step 1, step 2, come on, step 2. Then we have step 3 wherein we do data pre-processing. In this data pre-processing, first thing is to convert entire data into a common dimension. Example, all images to 28 by 28 by 1. Okay, this is achieved using reshape function. Second, we convert the input into float format. Convert input data into float 32 format. Why? Because weights with which you multiply the inputs will be in float 32 format. Next, you are going to divide or normalize the images to the scale 0 to 1. Why do you do this? so that weights converge faster to the minima. Okay. Once you do this, you basically specify your model, specify or design your network. You specify or design your network. Okay. Next, once you specify or design your network, you compile the model, network or model. Then you compile your model. Once you compile your model, you fit the model. Once you fit the model, you do something else of evaluating your model. Model on this data. Okay, so here I'm going to go to the code once again and explain these components also. All right. One more thing we forgot is we also have to deal with the output variable. Output variables should be in categorical. I mean, if they are in categorical format, like you have labels as 0, 1, 2, 3, 5, all those numbers. But then if you want to calculate the loss, okay, when you want to calculate the loss, and we discussed about this, yeah, categorical cross entropy, we already discussed. What did we discuss? Come, what happened? Okay, so that when you have your P, which is your actual data, and when you have your predicted data, Q, you'll have all those values, all the 10 values, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, you have 10, and then here also you'll have 10. Why 10 and 10? Because it's a 10 class problem, right? And say you have an image which is 9. So since there's a 9, what will happen in your actual data? It'll be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you have in this format, it doesn't work. So you need to convert this into one hot encoding format. One hot encoding means if you have 9 or 10 classes, you put all the 10 classes like that. And wherever you have this, for the first one, for the first entry, it is 5, right? So let me take this example rather than 9. So what you do is you put, it's not 0, it is not 1, it's not 2, not 3, not 4, it is 5. So for 5, you put a 1, rest all will be zeros. Same is the case with predicted values also. When you predict, you'll have probability values. Hey, there is 0.01% probability, 0.1% probability, 0.15, 0.18. In that way, you'll have the probability values. Okay, and here you'll get in that way. For this is for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, in that way. Yep, done. So you'll have all the probability values. When you add all these probability values should be equivalent to 1. Okay, say you get 0.1, 0.7% probability that it is, or 0.5% probability that it is 5. Now, what is cross entropy? A loss function which we discussed thoroughly summation of I equal to 1 until p or until n number of classes pi into log of qi. And you have 10 classes, so you'll say summation of I equal to 1 minus 10 pi into log of qi. If you substitute I equal to 1, it'll be p1 into this q1. Here we have q1. 0 into this will be 0. Then if you substitute I equal to 2, it will be p2 into q2. Then if you substitute I equal to 3, it will be p3 into q3, p4 into q4. All are zeros. p5 into q5. The only place which gets multiplied is p6 and q6 because it's 1 into minus 1 into log of 0.5. When you solve it, you get some loss. You take that loss, back propagate and update just to ensure that you can calculate this loss. You need the output variable in this format, in one hot encoding format, because only against that number you'll have a 1, rest all zeros, hence it's called as one hot encoding. Okay, that is the reason why we are taking this training labels, this data, and we are going to convert this to categorical format. That is the only reason. So you do that to categorical. So this is also another thing. It comes under pre-processing. After pre-processing, I think, mistake from my side, this is step 4. Then you have compiling the model as step 5. Then you fit the model, which is going to be your step 6. Then you evaluate your model, which is going to be step 7. Okay, so here one more thing that you do is convert output data into one hot encoding format. Why do you do it? We do it because we want to calculate the loss or cost function. And it warrants that your data is in that format. I've just explained that. Okay. Then the next step that I'm saying here is you need to specify or design your network, which we have already done here. We have designed the network. How many layers do we need to have? What activation function do we need to have? What should be the size of the input layer, size of output layer? All these things are done. So you define the model. So when I say define or specify the model, okay, dimension of input layer, dimension of subsequent hidden layers, or I would just say hidden layers. Then you define activation layers. If all you have any pooling layers, or if you have any striding, if you have any batch normalization layers, mention all of those. And then comes your output layer. This is called as defining or specifying your model. Specify or define or design your model. Once you do that, you compile the model. So that is what is something that we are doing here. As part of model compilation, you need to specify your optimizer What optimization function do you want to use? Gradient descent, right? Which one do you want to use? RMS prop is root mean square proportion. So propagation. So you're going to use that optimizer. Loss function is categorical cross entropy because we are dealing with multi-class problem. 0, 1, 2, 3 digits. Okay. And then you're saying I want to use a metric as accuracy. Metric is used to evaluate your model performance. Loss is used to optimize, right? Here optimization is to minimize your error or loss. Okay. Minimize categorical cross entropy. So three things: optimizer, loss, and metrics. Optimizer to be used, specify the loss to be optimized or reduced, then specify the metrics to evaluate the model performance. So you specify your or compile your model. Once you compile, you fit your model. When you fit your model, you give your inputs, which is training data, and you specify the number of epochs and specify the batch size also. So when you fit the model, specify the training data inputs and outputs or output. Then you specify the number of epochs. You know what? You can also specify the batch size, mini batch SGD in that way. And you also can specify various things such as the box, batch size, yeah, validation data. If you have any, if you have train, validation, and test. If it's only training and test, good. But then moving forward, what we shall do is we'll split the data, training data into training and validation. And we'll keep test data aside. We'll train the model, we'll test on the validation, we'll keep making changes to the hyperparameters. Once we get the desired result, then you're going to test on the test data for one final time. Okay, that testing on the test data for one final time is called as model evaluation. So I'll run this first. Modular fit, epoch 1 started. Is my GPU available somewhere? It's taking 7 seconds, 3 seconds, etc. Yeah, look at that 5%, 4%. So your GPU is getting triggered. And you have your accuracy 94 to 98 to 98, 99, 99.38. So accuracy is increasing at the end of each epoch. Once you build your model.fit, you are going to evaluate your model on the test data. So during your model evaluation phase, you specify the test data. That's it. And then you get the result. This is how simple it is. Okay, so you run it. You get loss and test both. Here you see loss, which is categorical cross entropy, and then accuracy. But we are interested in accuracy, so I'll run that. Here we have 0.99 test accuracy. So training accuracy and test accuracy, both of these are high and close to each other. Hence, we say that this is a right fit model for us. Okay, so I think now is the time that we take break. and it's almost 11:40. So we'll take a break until 11:50 and then restart the session. Please come back after the session. We will learn more about, we will take a few more images and then build this model. I'll be on mute. Yep. So we are back. Yeah. So Vagisha, you will have to relook at the recorded videos to get example of that. Yeah. Shakina, you're right. Okay. No, I've explained that, Vishnuvardhan. I think you have to relook at the recorded video once again about why do we do one hot encoding there. Then import is working directly, Sridhar, because it's already available in that particular library. So we are directly taking from there. Yep, we will see that. We will see that. Humira, Anil. Yep, it is compulsory that you convert. If your data is not categorical, you need not, because you'll use a different loss function there. All right, I think those are the questions. No, we do not have to submit any assignments, but you'll have to participate in the quizzes. All right. So just to do a quick, recap. This is what it is. CNN is used to deal with videos and images. You understand the business problem. You perform data collection. You perform the data pre-processing, specify the model, compile the model, fit the model, and evaluate the model. Done. This is exactly what we do. And now we are going to take this discussion further, and then we are going to learn about new things. So what we shall now do is we will understand about the convolution operation. Okay, and how did it operate basically? And what is the fundamental difference between densely connected layer and convolution layer? Within your MLP, you will have dense layer, and when it comes to your CNN, you'll have convolution layer. Convolution layers learn, okay, dense layers first. Dense layers learn global patterns because dense layers will consider the entire image. They consider the entire data basically, right? All the pixel values in some sense, right? So you take all pixel values in this example. When it comes to your convolution layer, you learn only the local patterns. Only the window, convolution window width, you consider only that. The key characteristic which makes convolution layer or convnets very different are two. Okay, convnets. Let me write it in this way. Are two. One is these patterns are translation invariant. Okay, translation invariant. And the second thing is they will learn spatial hierarchies. What does this mean? Translation invariant means, say you're looking at face of a person. In one image, Face was at the left top or top left. Face of the person was here. In another image, maybe the face of the person is here. It's the same person. In one image, it is at the top left. In another image, it is at bottom right. In both these scenarios, okay, in both these scenarios, face will be identified. Okay, hence it's called as translation invariant. Even if you translate the image to various corners, it will identify. That's the beauty. However, because what you're doing in ConvNet is you're just taking a filter of specific size, you convolve it throughout. But then when you use your MLP, what happens is your MLP will consider the global patterns. All the pixels are taken. So whatever pixels you have in this portion also would be considered. And whatever you have on this portion also would be considered. Hence, MLP would be time consuming process. Hence, CNN is much better, much faster to learn the representations of the data. Representations means features like pixel, intensity, edges, texture, blobs, so on and so forth. And the second thing is ConvNet also has another feature, which is they learn spatial hierarchies of patterns. What do we mean by that? If this is a human face, first it will try to identify the edges. Like you have an edge here, nose has an edge, mouth has an edge, eyebrows have edges, your jaw will also have edges. So all those edges are learned. Then the next convolution layer, what will it learn? It will learn patterns which are already made by the features of the first layer. So already it made these edges. Now what is the next thing? Next thing is what is there within those edges. So we have eye, we have a nose, we have a mouth. So in that way body parts are learned. This allows your ConvNet to learn even the complex patterns like cancer images, etc. in a very structured manner. Okay, so step by step, layer after layer, hidden layer, first hidden layer will learn edges, next hidden layer will learn the body parts or the components of the face like eye, nose, etc. Parts of your face, not components, my bad. And then the third hidden layer will learn the entire face, etc. This is how it works. So dense layer, global pattern, convolution layer, local patterns. ConvNets are different because of these two additional advantages. It is translation invariant and it learns the spatial hierarchies of patterns. Shall we make a note of that? Yes. So, model building overview of steps. Okay, now here advantages. CNN learns, I'll expand this so that it's easy for me to type. Local patterns as goes to MLP, which learns global patterns. Okay. Next advantage is that it is translation invariant, and the next advantage is that it will learn the spatial hierarchies of patterns. Okay, these are the advantages. Then we have a few other advantages. Just a moment, friends. Sorry, just a moment. Just give me a minute. Sorry. Yep, sorry about that. Okay, here. So a few more things that we need to learn about convolution layer is that convolutions operate on 3D tensors. These 3D tensors are called as feature maps. Feature maps has two spatial axes. Those two spatial axes are height and width. Okay, and it will have another axis which is called as depth axis, singular and plural, right? And this depth is nothing but the color channels, RGB, etc. Right? If you have a color channel, you'll have 3 channels, and if it is a black and white image or grayscale, you will have 1 channel. This is a most important feature. And then, of course, we have discussed about various things such as you define 2 things when you define your model. Right here, when you define your convolution layer. So here, I think we didn't mention that. Convolution layers. So in this convolution layer, you'll have 2 things. One is the size of the patch. Size of the layer, 3 by 3, 4 by 4, 5 by 5, etc. And then we also need to define the depth of the output feature map. For example, you mentioned, right, that you want to apply 32 filters. 32 con 2D filters. What is this 32 capturing? It's capturing the depth. Okay, it's the number of filters computed by the convolution. Okay, very, very important. These kind of things are extremely important. Then you also can mention or describe about padding. You know about padding already, right? So I'll put it here somewhere. Padding layer. This is also another layer kind of. It's an argument that you give within this. So I'll do one thing. I'm going to delete it here. And I'm going to add it here. When you say padding is padding has arguments, it takes one of two arguments. One is valid. When you say valid, that means no padding. There won't be any padding. When you say same, means it will automatically do the padding for you to ensure that the output is of same size as input. Okay, this is very important thing. And by default, it is valid. That means it doesn't do any padding by default. Here, striding default value is equal to 1. So you will always do a stride by 1. Okay. So this striding is also used to downsample your image. So let me put it here. It is also used to downsample, okay, your image. It will reduce the size of your image basically. And pooling layer also does exactly the same. But usually people use pooling. Okay, when you see in action. This will also downsample. Okay, and then you have max pooling, average pooling, and you have L2 pooling. There are also other options, but majorly max pooling is used. We just say max pooling 2D. Okay, so these are all the various benefits which exist. Now, I'm going to show you a couple of things. With max pooling, without max pooling, what happens is something that I want to show you here. We are defining the sequence model. This is just to show you on what will happen if there are no max pool layers. I'll run this. So you're using conf 2D 3x3. You're using the input layer activation function, the same thing what we have done earlier. I'm adding another conf 2D of 64 3x3 ReLU, and again I'll do this, and then you see a summary. So these are the weights which are learned parameters. Okay, now the final feature map that you have here is learning a lot of coefficient values, and when you take this 22 by 22 by 64, and when you supply this to a flattened layer, you'll have what? 22 by 22 by 64. You can multiply and see it will be approximately 20 into 20 into 60, right? 400. It will be approximately 3000. You just multiply and see. These, sorry, 30,000, my bad. 30,000. So approximately 30,000 will go to your dense layer, which will be huge. Okay, it will be very huge. And if you have 30,000, and if you are putting these 30,000, which is 22 by 22 by 64, and if you want to flatten it, then you multiply it, right? You flatten, and once you flatten, you'll get a layer like this, and you supply that layer to a dense layer of say 512. So 30,000 plus 1 bias into 512, the number of weights your model is going to learn will explode. Okay, it becomes exorbitant. You need huge, processing capabilities. On the other side, look at this thing. Same thing, 32 by 32 by 3, ReLU, and input image. Okay, and then I'm using conv 2D, 3 by 3, 64. So you have 3 by 3, 64 ReLU. Again, you're giving 64 3 by 3 ReLU. When you do this, when you solve this, you'll get an output. Okay, let us see how this output looks like and what will be the size which we need to flatten. Okay, so I'll just remove this and let's run this and see what happens. I will run this part. Look at this, 3 by 3 by 64. Wow, 3 by 3 by 64 is what you will flatten, and you're going to supply that to your dense layer, whatever bit. Even if you supply this 3 by 3 by 64, how many will you get? Okay, 3 by 3, 9, 9 into 64, or 10 into 64. Yeah, approximately 500 if you take 9 into this. Okay, or otherwise also, if even if it's 10 at 640, so it'll be very less into this. So even if it is approximately 600, 600 into 512 will be much less than 30,000 into 512. Look at the importance of having max pool layers. Do not take it for granted that this is there just for fun. No, by no means it is there for fun. There is a, you know, application of this, which is very, very important. Okay, that's the main thing. Now, we will switch our gears and learn about cats and dogs example. Let me see if this data set is the right path or not. Okay, so you have your training data wherein you have dogs. All these are the dogs that you have, and also you have cats. Okay, so you have dogs and cats. Since you have dogs and cats images, we want to supply this as an input to our model, and we want to thereon classify the moment a new image is supplied on whether that new image is cat or a dog. Simple. We are solving a very simple use case. So I'll just uh, erase all these things so that I free up some memory. And what we shall now do is, I'm going to first explain about this data set. Okay, this specific data set, a practical example for that case is to classify on whether your images are dogs or cats. And here we have in total 4,000 images, in which you have 2,000 dogs and we have 2,000 cats. Okay, and then what we are doing is we are taking this data set and we are splitting this into first training and test. Okay, so what we are doing is, again, the training data is split into training and validation. So we're going to have 2,000 images in training, 1,000 images in validation, and another 1,000 in test. Since we have cats and dogs equal proportion, 50-50, here also 1,000 images should be dogs, and another 1,000 images should be that of cats. Here in validation, 500 images should be dogs, another 500 should be cats. Here also 500 will be dogs and another 500 should be cats. So we learn about a lot of things here. We will learn about how do we build a simple CNN model. Then how do we use data augmentation to increase the accuracy further. Then since the amount of data is 4,000, this is considered to be a fairly small data set. If you have a small data set, how do we make use of pre-trained models as is, and how do we fine tune a pre-trained network? All those variants we are going to discuss. So let me put it here on what are the various things that we are going to discuss here. Building example. Okay, here what we will do is we're going to first run the model with the available data as is. Second, you run the model with the available data by performing data augmentation. Then run the model by extracting features from pre-trained model, pre-trained network. And finally, you run the model by extracting features from fine-tuned pre-trained network. So you fine-tune it to get a pre-trained network and then you proceed further. Okay, this is how it works. All these things and more. So this means end to end you would have learned majority of the things in CNN. I would not say all, because as part of our full-blown training, we actually train on PyTorch, TensorFlow. Majorly we use PyTorch, which is catching the attention of the world. And what we also do is we apply a lot of additional techniques. We build CNN, RNN model for image captioning, etc. We build 3D models to deal with videos, many other things, but this is good enough to a great extent. So you're importing OS and shell utilities, wherein you can define your directory, base directory, where you have your where is this? Yeah. Where you have your cats and dogs small. This is being treated as your base directory. Then you have your training directory. Within training, again, you have cats directory and dogs directory. So we are mentioning all that. So training data, validation, test. So we have within this, that's a base directory. Within that, you have the training directory. Same path is given. Then you have validation directory. Then you have test directory. Then if you get into training, you have cats and we have dogs. Then in validation also you have cats and dogs. Test also you have cats and dogs. You run that. Done. Directories are defined. Now I want to print the length of os.list directory. So what happens is in train cats directory. Let me go to cats directory here. So I'll go to train cats directory. If I just say I want a list format, I'll say view as a list. So these are all the list, right? So you want to count on how many images are there, basically 1, 2, 3, 4, 5 in that way. We have 999, but the count is starting from 0. 0 until 999 is 1000 images. Okay, so I'll run it and I'll say total training cat images colon what is the length of that list of the directory. It is 1000. So you have 1000 cat images. When you say total training dog images, and if you look at the OS length, you get another 1000. Then you have cat images in the validation, then validation dog images, then test cat images and test dog images. You run all of that. Okay. Then you're defining your model here. What model are you defining? The same thing which we have learned. We need to build our network. So we are using the input image. Input images are of size 150 by 150. You need to know this, right? You just import an image, it will give you on what is the size of that. You know how to import, right? cv2 dot image read that image. It will tell you what is the dimension of the image. Simple. Why 3? Because these are all color images. You're using a conv2d 32 3 by 3. You're using ReLU activation function. Because these images are very big, it really makes sense for us to use conv max pool combination. Okay, it will augment the capacity of the network by reducing the size of your feature maps so that it doesn't become overly large when you actually supply the data to flatten layer. Okay, so same thing, max pool 2D, then conv 2D, 64 conv 2D of 3 by 3. You're using ReLU activation function. And again, you're using a max pool 2D of 2 by 2. You're reducing the size of the image to half basically. Then you're using 128 3 by 3. Again 128, again max pool, so on and so forth. Friends, remember one thing, that how many you're going to have here, the count of the different convolution layers you'll have, the size of the convolution layers you're going to have would be different. Just give me a bit, extremely sorry. Just give me a minute. Sorry, so sorry. That was actually I could not avoid that. Okay, so here we have the data that we are taking in, and we are then flattening the data, right? You flatten the network, supply it to your model, then you supply it to the dense network with ReLU activation function. And why do I have a single neuron? Because it's binary classification problem, right? You need to classify on whether the image is cat or a dog. Since it's a binary classification problem, we are using sigmoid activation function. All these things we discussed, I request you all to watch the recorded videos again. And the reason why we are not providing you with the code is because we want you to type and practice. It's there on the videos. Please practice. Okay. So you have the data here. And then once you define your model, you need to specify your, or you need to compile the model. For that, I'm importing optimizers because I want to use an optimizer with a different learning rate. Remember learning rate? You can choose whatever learning rate you want. Here we are using 1 into 10 raised to the power minus 4. That is how you write this component, which will be 0.000411. Sorry. It's a very small learning rate. And we are using binary cross entropy because it's a binary problem and the metric is accuracy. So we have an optimizer. We will run this, compile the model. Okay. And then we are going to use image data generator. This is also another way to resize your image, and you're dividing each value by 255. Okay, this is yet another way to actually pre-process your images. So currently the images that we have are on the drive here, on the shared drive here, and all these images are of JPEG format. You can just right click on one of those images, look at the properties. It's JPG format, which are RGB, red, green, blue, color images basically. We want to convert these into floating point. We need to rescale the pixels to 0 to 1. Okay, so we know these things. That's the reason why we are doing rescaling, etc. So we are pre-processing the image. We are importing image data generator, and we are rescaling this to 1 by 255. Okay, and then what we are doing here is, these are fine. Next you're saying go to this entire flow of directory, entire training data of all the images, go to the training directory. Basically you resize all the images to 150 by 150. This is also something that we already discussed on why we need to resize the image. Okay, and then you want to resize it in batch of 20. Take 20 20 20 images and resize them. And then because you're using binary cross entropy, you're saying class mode is binary too, cats and dogs. The same exercise is being reported, or the same exercise is being performed on your validation directory also. You run it. So you have 2000 images belonging to 2 classes. In training, in test, you have 1000 images belonging to 2 classes. Done. Pretty simple, pretty straightforward, right? All these things, whatever we have discussed, the same things are being repeated. Okay. This part is not needed, this label encoder, basically. So I think I would skip that part. Not needed, so I'm skipping that part. I'll also remove this code, but it's there just in case you want to see on what it exactly does. And then you're saying model.fit underscore generator. So you want to fit your model. Okay, until here we discussed in the previous thing. Underscore generator is when we run this particular stuff, you also have to pass your validation data. So you have your training generator, all the training data would be there, and then you have validation generator, which will have the validation data. Okay, for the if you use dot fit, this validation data is not needed, but here this is needed. Okay, if you pass this validation data, then your generator is expected to also give you validation data. It is expected to train the model and at the same time test on the validation data. And the validation steps here tells the process how many batches to draw from the validation generator for validation purpose or evaluation purpose. You don't want to use complete validation data. You want to use 50 images. After that, take another 50 images. After that, do another 50 images, right? It's like instead of lifting all the 100 bags at one time, you are lifting 10 bags, 10 bags, 10 bags each time. It's easier, right? That's the reason. So let me fit the model. Now, this GPU will come into picture. We'll have to wait until this process completes, and 14% of GPU is being used. I'm sure if it was a powerful GPU than this, it would have done wonders. Number one. Number two, if you use PyTorch, then it'll be even faster. Okay, so for the first time, accuracy is so much, validation is so much. So what we will do now is it will anyways, there are 30 epochs, and even if it takes 30 seconds each, then it'll be 15 minutes or so. Yeah, or 19 seconds. So it will take at least 10 minutes. So in these 10 minutes, it's anyways around 2:35, 12:35. Let us take a break until 12:45. By the time we are back from the break, this will be done and we will be looking at the end result. Okay, let's take a break and come back. All right, so let's discuss further. Yeah, so model will automatically take care of that, Samasiva Rao. Okay, your model will automatically do it here. All right, so if your question is on this test data, oh, okay, you're speaking about test data, I believe. Yep, we'll get there because we need to now test it on the test data also. Okay, we'll evaluate it. So what you do is basically after you build your model, you use this function called model.evaluate and you evaluate on the test data. So the basic premise that is probably not coming to light in your understanding is we have data, we are splitting that into training and test data. Then we are splitting this further into training and validation. Okay. Now what we have done is we have built the model on the training data and we are validating on the validation data or testing on the validation data. So you get the validation accuracy and the model that you built. Okay, the model that you built is also tested on the training data. So here is the accuracy of the training data. So you take the training data accuracy, validation data accuracy, and look at what's happening basically, right? Even before that, the moment you build your model, it always makes sense to save that model. Okay, good that you built your model, but then we need to save the model for future use. So you're doing here model.fit, right? So model.fit, you're building your model and then you're saying model.save and you're going to save your model. When you save your model, there are two ways of saving your model. One is in H5 format, another is HDF5. So we are saving the model. And when you say model.fit generate, you are storing the results in history. This history has four things. One is loss, that is training loss, accuracy, training accuracy, validation loss, and validation accuracy. These four are stored. Now I want to display the results, visualize the results, and take it further. So what we are doing is import matplotlib as PLT. Matplotlib is a data visualization algorithm that you have, or library that you have, sorry, data visualization library. And I'm saying history dot, within history, you're storing it in history. You can also store this in another object called ABCD. Then you, if you say ABCD dot history, history has accuracy, which is training accuracy. You store it here. This ABCD also has history, validation accuracy. Then this has loss and it has validation loss, all four. You take all those four things and then you say range of 1 comma length of accuracy plus 1. So 1 until length of accuracy means you have 30 accuracy values plus 1. And then you say plot epochs. Here on x-axis you'll have epochs and on y-axis you'll have accuracy values. BO means blue color circles and the label is training accuracy. Then you're going to plot epochs on x-axis, validation accuracy here, and you want a blue color line, and you want a label as validation accuracy. Overall title of your plot would be training and validation accuracy. Plot.legend means it will give you a legend here saying that this blue circles is training, this blue line is validation, and you want to see the figure. Let me run this. There we go. Okay, so what's happening? You have the training accuracy, validation accuracy. When you look at the training accuracy, it kept on increasing, but validation accuracy after maybe sixth epoch or so, it more or less got stabilized. So here, after this fifth or sixth or seventh epoch, your model is overfitting. So you're not even happy about the, so you have the data, you split that into training and test data. You split this further into training and validation. And we built the model using the training data. And you test on the validation data. And then you get validation accuracy. And your model by default will test on the training data also. And then you'll have training accuracy. Both of these, right? So here, you're not satisfied because training accuracy is training accuracy is 99%, 0.998, and validation accuracy is only 0.719 or 72%. There is a huge difference. So what should you do? You have to again go back and make some changes to the model that you're building. And then again test on the validation. Until and unless you're not happy with the validation accuracy, you cannot test on the test data. Doesn't make sense. Okay, so first go back now with this because you're unhappy, and then tweak your model, tweak your hyperparameters, then again come back and test on the validation data. So we'll continue doing that tweaking of the hyperparameters until we are happy about the model that we built. You can also not just plot the accuracy values in that way because you have all the epochs here. Epoch after epoch after epoch, training accuracy is increasing, but validation accuracy is staying constant. Okay. You can also try with loss. So here you have number of epochs, loss. Blue color circles, label is training loss, validation loss. You can also do this. Again, extremely sorry, you just give me 2 minutes time, please. about that. Yeah. Okay. So there are certain questions which are being asked here. Let me look at those. One is, will the weights learning happen while the no, weights learning happens only during the training. Another question is, um, yeah, Rajkumar, we have a program. I'll just briefly show you that. So when you go to 360 Digit MG, when you go to courses, you have domain analytics. Within domain analytics, we have cyber security analytics. And do you know what? We have 56 plus domain analytics programs. We also have construction analytics for civil engineers. And then we have manufacturing and automotive analytics for mechanical engineers. For people from biopharmacy, biomedical, uh, BDS, etc., life sciences, healthcare analytics, MBA finance, BCom, etc., we have financial analytics, accounting, we have internal auditors, right here, data science for internal auditors, many things. Digital marketing, we have social media, web analytics, all about data science, etc. Okay, so that aside, mm, question here is okay. So I'll answer Mr. Murthy's question. This is nothing but on this. What happens is indexing in Python starts from 0. Okay, indexing starts from 0. So here you have 0, 1, 2, 3, all that, right? So even if you say range of 1 to length of accuracy, what will happen is 1 means it will give an index number 0. 0 until length of accuracy. How many accuracy values will you get? 1 accuracy per epoch. You'll have 1 accuracy per epoch. Epoch number 30 means you'll have 30 accuracy values. So if you say 0, I mean, this will start from 0. And if you say length is 30, do you know what? In Python, two things. One is indexing starts from 0. Second thing is this last number will be ignored. You can just try out 0:4. What it does is it will take 0, 1, 2, 3, and it will ignore this fourth last one. Hence, you're adding length of accuracy plus 1. Just to ensure that number 30, if you give 30, it will ignore 30. 30th epoch will be ignored. If you say 30 plus 1, it will be 31. So 31st will be ignored, and until 30, you'll have everything. This is one thing. Okay. And the next thing is, yeah, we will provide you, Rajkumar, with the details. Then, will the weight learning happen? No, weight learning will happen only on training data. Then the next question is, I'm asking, how do you give to the model random test means which doesn't have any label, because model requires both image and label. Shamasiva Rao, for that only I'm telling you that you first build your model on the training data, okay, and then test on the validation data. And then you also have test data here. Why are you discussing about test data when we still are building the model here and testing on the validation data? That's one question that I would obviously have for you. So just clarify me that, because maybe you're getting confused. Okay, how do you give the model random test means which doesn't have any label? What do you mean by that? I didn't quite get you. So here, when you train your data, you're training the data on both your X and Y. Okay. When you're testing on validation, how do you give only X? Is that your question? If this is your question, then my answer to you is, I'm just giving this directory. Okay, I'll go here to the directory. In your directory, clearly, when I go to train, you have dogs and cats, the names of the folders. These are taken as the output. Okay, if that's your question, that's my answer. If not, you can call me on my number. We will talk. Okay, sure, we will do that. Then what is the use of calculating the loss while validating burning? Oh my God. Okay. So when you test on the validation data, by default, it is going to calculate the loss. There is no mechanism to stop it. Okay, you have to remember that. Only during the training, it is going to calculate the loss and get here. And when you validate, just because it's there. And why is it there? Because you also want to, you know, display your loss functions to check whether your model is overfitting or not. So here you have training loss and validation loss. Okay, training loss and validation loss. If you want to evaluate whether your model is overfitting or not, you can either look at the accuracy values, or you can look at the value at the loss values to decide whether your model is overfitting or not. Choice is yours. Just because it doesn't cost anything for calculating the validation loss, it's calculated. It's up to you on how you want to analyze. Then can you take a digit which is not a 28 by 28, classify it for cats and dogs problem? Random test means which doesn't have any label because model requires both image. I think you're confused. You can call me Samasivarao. I'll talk to you and explain you clearer. Okay, how to change the values of weights in validation accuracy is not satisfied. Okay, I think too many questions. Our team will respond to that. A few I feel are related to the previous videos. Show me example of something else apart from images. Already, all these days we have done that. So it's there as part of the previous recorded videos. You can watch that. Okay, let me move on. So now what we are going to do is, since our model is very clearly overfitting, after how many epochs is it overfitting? After probably 6 epochs, your model is overfitting. Okay, since your model is overfitting, we can use a lot of regularization techniques, such as where are the regularization techniques? Yeah, here, overfitting. You can try out early stopping, you can try out dropout. Okay, you can try out weight optimization, L2 regularization, weight decay. There are many techniques which exist. They did not include the weight decay here. I think I didn't. So I should have done it. All right. So I will quickly add it here. So every day after the training, I'll get the new version updated so that you all learn from it. So here we also have weight decay. In weight decay, you have L1 regularization, which is called as lasso. L2 regularization. Okay, and there is also data augmentation technique, which is very, very helpful when you have images. When you have images, simply put, you can do your data augmentation and it will do wonders for you. And here, the data augmentation that we are doing is, uh, there are many things that we are trying out. One is rotation range is 40. It actually ranges from 0 to 180. Within this range, you can randomly rotate the pictures. When you say 40, your images will be rotated by 40 degrees. Width shift, and you have height shift. So what is the fraction of total width or height within which to randomly translate the image? Meaning, if you have an image like this, how do you want to translate your image? Along the width or along the height is something that you need to decide. Then you have something called as shearing transformation. Shearing transformation is yet another transformation which is similar to your the projective transformation, or it will be like this. For example, if this is the image, right, you'll make your image like this. Image like this. This is called as shear transformation. You can zoom your image. Okay, you can zoom it by 20%. Then you can horizontally flip your image. And when you apply all these rotation, height change, width change, etc., there might be new pixels which might get created. How are you going to fill those new pixels? You're using nearest neighbor technique. Yeah. So all these things we can do. This is why we have looked at OpenCV. Okay, so I'm gonna run this. Then what we are going to do is we are going to choose this image module, which is used for pre-processing. Then you say os.path.join. You're taking the training cats directory and the file names. Okay, and you're taking for file names in OS list directory, your training cats directory. In short, what you're doing is you're going to your training cats directory, you're taking each and every name, and then you're combining all those file names. If I simply say, take the image path, choose one image, say I'm saying file names of 3, it will show me the third image. It will take the third image basically, and then I'm going to take that third image. I'm going to ensure that the size is 150 by 150. So you resize the image. Then you convert the image to 150 by 150 by 3. And then you're going to reshape the image here. You're taking one image, you're making it 150 by 150 by 3. Now what we do is we're going to say that we are going to do data augmentation on this using this function. So I'll just run it. Look at that. See, one more thing that you guys have to remember is this learning programming will not happen overnight. Overnight, you cannot learn, right? It will take its own time. So you have to pay, that time, dedicate that much amount of time. Okay, here you are translating, and then we are doing nearest neighbor, right? So the last pixel is taken, repeated, all the missing things. Here you're translating the image, and Here you're rotating the image. Here also you're translating or flipping the image, right? All these are the various image augmentation techniques that we are applying. Now, once those things are done, you have to rerun your model. What I shall do is I am going to again take this defining your model stuff and compiling your model stuff, and let's redo this part. I'm going to take the same model. I'm going to specify the same model. All these layers, conv, max pool, flatten, dense, so on and so forth. And I'm going to add one additional thing here. And that additional thing would be dropout. I'm going to add another layer here, and I'll say layers dot dropout. We discussed about dropout already. It's 0.5. Okay, so you're defining your model. The summary is not needed basically here in a different way. Then once this is done, you need to compile your model. Okay, so I will go here. I'll say, okay, let's take this and let me compile the model. Same binary cross entropy, same optimizer, same accuracy. So done. Compilation is also done. And then we need to train our model on augmented data. So you have this image data generator, which we have come up with. Okay, so you will take this, and what I shall now do is I'm going to do a augmentation on the training data. Same thing, but then there are a few new things that I'm going to add here. I want to rescale the data. Okay, and then I'm also going to convert that into a float format by just using this dot. I'm rescaling this image. I want to rotate it by 40 degrees. All right. I want to shift by 20 degrees width, shift height by 20 degrees, shear range is 20, zoom range is 20, and then horizontal flip equal to true. And you put your nearest, you fill it with the nearest neighbor, whatever additional pixels get generated. Then you also do certain modifications on your training data. Validation data should not be augmented. Remember that. You're augmenting just to ensure that your model doesn't overfit. Okay. Validation data or test data, you won't do anything, any augmentation on that. Okay, only on the training data we do augmentation. Here I'm just rescaling the images. That's it. So we run these. Done. Then what we want to do is train underscore data generator. We have here. Okay. So I'll copy this. If there are any changes, we shall do it. and you have the training data. You are ensuring that the target data is of this size. You can change the batch size, any batch size. And then we are saying class mode is binary. So let me run this. Then what we are doing is we are doing validation uh, generator. We are applying that. We are ensuring that here also batch sizes. We can change batch size. You all know about that better than me now, right? So we run this data generator just to ensure that all the images are of the same size, etc. So here you have directory, you have the target size image, etc. Now history. I'm going to fit the model. We can also save this model for future purpose, but then train generator. Okay. And since you are using the entire directory here, folder name will be your output variable, and within that folder name you'll have the input variables, which are images. I'm going to reduce this by 100. You can also increase the number of epochs or let it be the same. And then validation step is 50. So I will fit this model now, and let's see what happens. The GPU has kicked off. I'll just wait for 2 epochs, and if this is going to take more time, not a problem at all. Okay, in the interim, you guys have a lot of questions. I'm going to help you with those questions. Okay, let's see. This has taken 26 seconds approximately. Second epoch, how much time does it take? Not sure. Let's see how much time it takes. Pose this, ask your questions, but I'll be answering it judiciously. 24 seconds or so. So it will take some time. It might take more. So let me go back here and ask or get some clarity. Yeah, a few of your previous questions I would have missed out maybe. So let me. Can I do the dog sketch data by converting to grayscale images? Which are the difference between both of those? And what is the role of LXNet in these examples? LXNet will just give you the architecture. We'll see that, Nagendra. Tomorrow, we will use a pre-trained model. Increasing number of max pool layers, is there any disadvantage because of the max layer? There's loss. No, Samasivara. How it works is, already you have extracted the data, low level details from the initial layers. So in the future layers, in the subsequent layers, so let me put it here, maybe. So let me yeah. See, what's happening is your initial layers will already capture the low level features. So you need not have the same big size image to extract the mid level features and high level features. Okay, so low level features means detailed features. For that you want entire image. High level means only at a high level you need features. Even if the image size becomes smaller, you'll still be able to extract the features. Okay, that's the point. So hope that answers your question. Tomorrow we will make use of pre-trained models and the AlexNet, etc., VGG16. There are a lot of models. We'll discuss those. It's not residual network, Ajay. It's AlexNet is a different architecture. ResNet is different. You can use inbuilt magnifier to show output console clearly. Uh, Let me check that, Usman. Yeah, yeah. Error plus accuracy is equal to 1. Loss plus accuracy is not, Jagdish. Loss is different. Error plus accuracy will be equal to 1. Loss is different. It's used for optimization. Plus accuracy, if you're saying should it be equal to 1, this is no, this is right. MNIST can be used, yeah. But will it give good results is a question that we need to ask. You can. Yeah, I'm just sharing a white screen and I'm writing on that. AlexNet is, yeah, old model. Now there are a lot of new architectures which are available. Rajkumar, you have been asking that question time and again. Go to YouTube and go to our recorded videos, AI videos, YouTube channel, and watch the previous videos because on ANN and MLP, we have used concrete dataset. Okay, Rajkumar? Question time and again. I'm just clarifying it. No, that might not be possible discussing the quiz questions. That's out of scope. No, Mr. J, that would not be possible. This code, Jagadish, if you run on CPU, it will not work. You'll have to run on GPU. Run on GPU. Rajshekar, the network that we have just built is your own network, right? Your own neural network. We defined the neural network here, right? In the code. This is nothing but you have defined your own model here. We are not using any pre-trained model. Hope that answers your question. Is there any possible? Yep. What are the features we'll consider to classify? Edges, blobs, textures. It is black box, Lalita. You really don't know what other features it extracts. How many epochs we need to run? Number of epochs depends on. It's up to you. It's experimental. No, quiz questions. I'm extremely sorry. We cannot discuss those because we want to use the same quizzes for the other students also. If we give the answers, it doesn't help. Material is there on a learning management system? Yeah, you can, Dr. Panduranga. You can convert GVN ready. Because Ananda, we want to have the traction on a social media only. So we cannot create online. It's an additional effort for us. Can you show once? Yeah, sure. Tomorrow I will show you, Anil, on how to use Google Colab. CPU, it won't run, Panduranga, unfortunately. For images, it won't work. No, it won't be undersampling, Jose. If you feel it's undersampling, then your model will underfit. Same code. You need not change it. Same code. You can watch this recorded video, Kanaka Kumari. It will help. Images, videos, you choose Ajay. You choose CNN models. For your structured tabular data, you choose ANN or MLP in that way. Okay, so here is a recorded video. all these videos. Just watch it once again. A few of your questions will get answered. And you were asking about Google Colab, so I think I can just show you briefly on what is Google Colab. Okay, you can just create your own new notebook if need be. That's it. You open it, you create a new notebook. It's taking a while, not sure why. Yeah, you just type 1 plus 1 and click on run here. It will give you the output. Okay, this is for free. You can save it. You can do many things. I'm not sure why it is taking so much of time. Answer is 2. But then you can do one more thing. You can say manage sessions, and you can terminate it if you're done with that. But then change runtime type. Here we are not using any hardware accelerator, but you can do a drop down and select a GPU or a TPU, save it. Okay. Now if I were to run 1 plus 1, it should be fast. So it was faster than the previous. Now if I change the runtime type to TPU, okay, and if I add a code, it should be even faster in that way. You, whatever code you're running, right, you just add the code here. For example, if you have this, you just copy that, paste it here, run it. Okay, and look at that output. This is how you run it on GPU. That's it. It's as simple as what you're doing here. Same thing. You just copy and paste there, it will start running. So we are still at 66th epoch, or sorry, 26th, 27th epoch. It might take another 3 minutes or so for me to complete this. In the interim, here we go. Subscribe to the YouTube channel if you are interested. Word with that. And you can, Srinivas Rao, you can work on OCR Telugu also. Yeah, I've shared the link for watching today's. Will AMD GPU work on? Yeah, it will work. Any GPU will work. Siddharth. Can we run this on shared GPU? And yeah, dedicated GPU will be faster. Shared GPU will be a little slower. Okay, Vijay Lakshmi, what do you want to know? Tell me. Apart from images, what do you want to know? Because CNN can handle only images and videos. MLP ANN can work only on your structured data. We have looked at the concrete data set and we have learned. What else do you want to know? Vijay Lakshmi. RNN models, we will deal with sequence data. Okay. So what else do you want to know? Tell me. You have structured data, we have worked on that. CNN, RNN, we have worked on that. Textual data will work on RNN, right, Kishore? Because we cannot implement CNN for text. I cannot implement, CNN for any other data. So hence we have to complete first images and then we have to move towards text, right? Text is part of RNN, recurrent neural networks. No, Jose. NVIDIA MX250 is, I think, the basic version that might not work for you. But however, it will work if you try Google Colab. I think you should try Google Colab. Yeah, you have Jupyter, you have Spider, you have Google Colab also. You have many other things that can be used. That's again images, right, Kishore? On one side, you're saying No, some other application we want to know, and on other side you are seeing this. Quite contradictory, Kishore. Okay. Uma Devi Deva says, sir, can you explain about GitHub? Yeah, sure, Uma Devi. We will. In fact, the images that I'm showing, cats and dogs, it's very large. I mean, it's very large in size. So we will look into that. We will, Sampath. That is there in the curriculum. We will touch base. We will look into GANs. MLPs will come in RNN. We'll look into that also. You can run in Spark also. Yeah, NVIDIA GeForce 1050 Ti will work. No, deployment is not discussed. It's not within the scope. You can run the code in Colab. Yep, Ananda Babu. All right. So I think we just completed this 30. So validation accuracy improved to 78. Earlier it was 71, if you remember. Now it increased to 78. Okay. And your accuracy, training accuracy from 99, it came down to this. So I will just run this code and you'll have better understanding. I can run this and show you a comparison between number of epochs and training accuracy and validation. It is not overfitting. Look at the magic of your model. It's not overfitting. Even if you can look at loss, it is not overfitting. Wonderful, right? So you can also increase the number of epochs because both training and validation accuracy is increasing, loss is decreasing. So you might want to increase the number of epochs and see whether it's going to further improve or not. So this is something that we will do tomorrow by increasing it to 100 epochs, and we will see how a model is going to work well. So Mr. Srinivas Rao, you have to go to YouTube channel and look at it. I posted. Just click on that. All the previous recorded videos are there in that. Text classification you can do, but people won't do it, Ramesh, using CNN. You shouldn't be using regular data, Ratnakumar, on CNN. CNN is something which will learn only images, right? LSTM models we will learn multiple object trapping. Yes, we can. Yeah, we can discuss later, Kishore. I mean, those are all discussed as part of a full-blown training. You might want to enroll there. Yeah. Yeah, code is there in the recorded video itself. You can watch it and you can rerun it. All right, friends. Thank you so much. We will again connect tomorrow and take it further. Thank you all.